In this video, I want to start with a little bit of motivation. So I want to look at the matrix A equal to 7, 2, -4, 1. And I want to think about how we would do calculations with matrix multiplication. So if I wanted to define a power, I could say A squared would be A times A. That seems pretty consistent with how we define powers so far. So this would be 7 to -4, 1, which would be times 7 to -4, times 7 to -4, 1, which would be, well, 7 times 7 is 49, minus 8 is 41. 7 times 2 is 14, plus 2 is 16. -4 times 7 is -28, minus 4 is -32. -4 times 2 is -8, plus 1 is -7. And so we can calculate that A squared is 4116 -32, 7. And when we do this, we've calculated A squared. But if I wanted A cubed, that would have to be A times A, which would be A squared times A. And I would have to do this process again using this new matrix A squared and multiplying by A. And this is a long, drawn-out process. This is going to take a long time to do. I would like a better way to calculate the powers of matrices. And that is sometimes doable. So let's look at a different matrix. I'm going to call this matrix P. And the matrix P is going to be the matrix 1, 1, -1, -2. And if I look at P is invertible. And so to calculate the P inverse, what I do is I go 1, 1, -1, -2, and then write my identity matrix 1, 0, 0, 1, and I row reduce this to get the identity matrix on the left, and the inverse matrix will be on the right. So I'm first going to subtract the first row, add the first row to the second row. So I get 1, 1, 1, 0. And when I add the first row to the second row, I get 0, -1, 1, 1. And now I'm going to add the second row to the first row, which is going to give me 1, 0, 2, 1, 0, -1, 1, 1. And then I multiply this second row by -1, which gives me 1, 0, 2, 1, 0, 1, -1, -1. And so P inverse is equal to 2, 1, -1, -1. And I care about P inverse because, or P and P inverse, because it just so happens that if I take this matrix P and I take another matrix that I call D, which is a very nice matrix. It's the matrix 5, 0, 0, 3, this diagonal matrix. If I take P times D times P inverse, I'm getting, well, P times D is going to be 1, 1, negative 1, negative 2 times D is 5, 0, 0, 3 times P inverse. I'll leave that like that for the moment because I'm going to do these calculations one at a time. I get 1 times 5 is 5 plus 0, I get a 5. 1 times 0 plus 1 times 3 gives me a 3. Negative 1 times 5 gives me a negative 5 plus 0. And 0 minus 6. And then I multiply that by P inverse. When I'm multiplying that by P inverse, I'm multiplying it by the matrix 2, 1, negative 1, negative 1. And when I do that, I get 10 minus 3 is 7. And then I get 5 minus 3 is 2. And then I get negative 5. Then I get negative 10 plus 6 is negative 4. And negative 5 plus 6 is 1. And the thing that's nice about this is that's A. So I can rewrite A as P times D times P inverse. This may not seem like a super valuable thing yet, but what if I wanted to calculate A squared? Well, that would be A times A, which would be P times D times P inverse times P times D times P inverse. P inverse times P is just I. So this is equal to P times D times D times P inverse, or P times D squared times P inverse. And in fact, if I wanted A cubed, this would be P D P inverse times P D P inverse times P D P inverse. And if I wanted A to the fourth, it would be P D P inverse, P D P inverse, P D P inverse, P D P inverse, etc. I could do this for any power. The thing that's nice is my P inverse P's in the middle always cancel out. So I get P D cubed P inverse, or P D to the fourth P inverse. And if I wanted A to the kth power, no matter how high k is, I get P D to the k P inverse. That's a really valuable thing because if I have a diagonal matrix like D and I raise it to any power, let's square it first, what I get is A squared 0, 0, B squared. And in fact, that happens for any power that I go. So if I take A0, 0, B and raise it to the kth power, this is just equal to A to the k, 0, 0, B to the k. So it is easy to raise diagonal matrices to high powers. And since I've got this P, D, P inverse is equal to A, I can take and carry out that calculation by just raising the numbers to the power and then doing two matrix multiplications. It is a much, much, much faster way to take a matrix to a high power. So hopefully that motivates the idea of why we might care about being able to rewrite a matrix A as something like PD P inverse, where D is diagonal. This only sometimes happens, though. It's only possible sometimes. And so this is a process called diagonalization. And there is a theorem about diagonalization that says an n by n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. And in fact, the A equal PDP inverse, if this is possible to do, then the diagonal entries are the eigenvectors of A. The diagonal entries of D are the eigenvectors of A. Eigenvalues of A. And the columns of P are eigenvectors of A. So to do this, carry out this diagonalization, we have to find the eigenvalues, find n linearly independent eigenvectors, one associated with each eigenvalue, and then write P as those eigenvectors as columns, and D is with those eigenvalues as diagonal matrices. Let's do an example. Say A is equal to 1, 3, 3, -3, -5, -3, 3, 3, 1. If this is our example, we start out by finding our eigenvalues. So I need to take the determinant of A minus lambda I and set that equal to 0. So let's find first the determinant of A minus lambda I. Well, A minus lambda I is 1 minus lambda, 3, 3, -3, -5 minus lambda, -3, 3, 3, 1 minus lambda. And if I take the determinant of this, I'm going to get, the process is long and drawn out. There's a few different methods that you can use to do this process. And some of them will make it faster. But the point is, this process, taking this determinant, is unfortunately not easy. easiest method for doing it would involve doing row reduction and things along those lines. You can also do it through cofactor expansion, doing like, so this determinant of a minus lambda I through cofactor expansion is going to be 1 minus lambda times the determinant of the submatrix, which I'm just going to use the vertical line notation for determinant, negative 5 minus lambda, negative 3, 3, 1 minus lambda, minus 3 times the determinant of the remaining pieces. I'm going across the top row, so the remaining determinant would be negative 3, negative 3, 3, 1 minus lambda, plus 3 times the remaining determinant would be negative 3, negative 5 minus lambda, 3, 3. Then you would have to do the determinant of each of these things. So you'd get 1 minus lambda times negative 5 minus lambda times 1 minus lambda minus a negative 9 becomes a plus 9. Minus 3 times negative 3 times 1 minus lambda minus a negative 9 is plus 9, plus 3 times negative 3 times 3 is negative 9, minus 3 times negative 5 minus lambda. Then you have to multiply this all out and simplify, and the process gets long and drawn out to do that, but at this point it's just a lot of algebra. But if you do all of this, you get negative lambda minus 1 times lambda plus 2 squared. Which means that our eigenvalues are lambda equal 1 and lambda equal negative 2, but this one is repeated. So that one is occurring twice. So we hopefully will be able to find 2 linearly independent eigenvectors for lambda equal negative 2. So let's see if we can do that. So the first piece is I'm going to rewrite my A. And the eigenvalues I had were lambda is equal to 1 and lambda equal negative 2, with this one being repeated. So let's first deal with lambda equal 1. So I want to find some vector x such that a times x is equal to x. So I'm dealing with, I'm going to write my x as x1, x2, x3. And so then I get that 1, 3, 3, negative 3, negative 5, negative 3, 3, 3, 1 times x1, x2, x3 is equal to 1 times x is x1, x2, x3. So now I have the equation x1 plus 3x2 plus 3x3 is equal to x1, negative 3x1 minus 5x2 minus 3x3 is equal to x2, and 3x1 plus 3x2 plus x3 is equal to x3. Taking these, I can subtract x1, x2, and x3 from both sides to get the system of equations that looks like 3x2 plus 3x3 is equal to 0. Negative 3x1 minus 5x2, minus 6x2 minus 3x3 is equal to 0. And 3x1 plus 3x2 is equal to 0. This gives me the augmented system of the augmented matrix 0, 3, 3, 0, negative 3, negative 6, negative 3, 0, 3, 3, 0, 0. I need to row reduce this, so I am going to switch. Let's just switch rows 1 and 3 to get 3, 3, 0, 0, negative 3, negative 6, negative 3, 0, and 0, 3, 3, 0. I'm going to multiply that first row by negative 1/3, by 1/3. And while I'm at it, I'm going to I'll just do that one for now. So I'm going to multiply the first row by 1/3. And I'm going to also add the first row in its current form before the multiplication to the second row. So that gives me 1, 1, 0, 0 in the first row. In the second row, it gives me 0, negative 3, negative 3, 0, and 0, 3, 3, 0. Now I'm going to multiply the second and third row by negative 1/3 and 1/3, which is going to give me 1, 1, 0, 0, 0, 1, 1, 0, and 0, 1, 1, 0. Adding the adding negative 1 times the second row to the first row gives me 1, 0, negative 1, 0, 0, 1, 1, 0, and 0, 1, 1, 0. Now, I am left with taking the third row and adding negative 1 times the second row to it, which gives me 1, 0, negative 1, 0, 0, 1, 1, 0, and 0, 0, 0, 0. Which means that my x3 is going to be a free variable, and x1 minus x3 equals 0, x2 plus x3 equals 0, and x3 is free. So x1, it has to equal x3, and because of the first, so x1 equal x3, x2 is equal to negative x3, and x3 is free. So one eigenvector, the eigenvector associated, or an eigenvector associated with lambda equal 1 is going to be plug anything I want in for x3. I'm going to pick 1, and I'm going to get the vector 1. x2 is negative times that, negative 1, and x1 is just the x3. So we have our first eigenvalue is lambda equal 1, And we have associated with that the eigenvector v1 is equal to 1, -1, 1. Now we still have to deal with the eigenvalue lambda equal -2. So we're going to do the same basic process. We're going to take that same A is equal to 1, 3, 3, -3, -5, -3, 3, 3, 1, and say A times x, so 1, 3, 3, -3, -5, -3, 3, 3, 1, times x1, x2, x3 is equal to -2x1, -2x2, -2x3, which gives us the equation x1 plus 3x2 plus 3x3 is equal to -2x1, and -3x1 minus 5x2 minus 3x3 is equal to -2x2, and 3x1 plus 3x2 plus x3 is equal to -2x3. Adding the 2x1 and 2x2 and 2x3 to both sides of these equations gives me 3x1 plus 3x2 plus 3x3 is equal to 0. -3x1 minus 3x2 minus 3x3 is equal to 0. And 3x1 plus 3x2 plus 3x3 is equal to 0. This gives the augmented system of the augmented matrix 3, 3, 3, 0, 3, 3, 3, 0, 3, 3, 3, 0. Finding the reduced row echelon form of this is fairly straightforward. It is 1, 1, 1, 0. And then using that first row, I can zero out everything below it. So what I have is x1 plus x2 plus x3 is equal to 0. x2 is free, and x3 is free. Or put another way, x1 is equal to -x2 minus x3, and x2 and x3 are both free. Which means I can pick values for x2 and x3 and then get the value for x1. So let's pick for one of these vectors. x2 is 1, x3 is 0. So that would make that x1 has to be -1. And there's an eigenvalue associated with -2. Or I could pick a different eigenvalue. I'm going to pick 0, 1 for x2 and x3, which makes x1 -1. And so now I have 3 linearly independent eigenvectors corresponding to my eigenvalues. So with lambda equal 1, I have the eigenvector 1, -1, 1. For lambda equal 2, lambda equal -2, I have the eigenvectors v2 is equal to -1, 1, 0, and v3 is equal to -1, 0, 1. So I can define my P and my D. P P is going to be equal to the matrix formed by where the columns are these eigenvalues, v1, v2, v3, which if I write that out is 1, -1, 1, -1, 1, 0, -1, 0, 1. And D is the diagonal matrix with diagonal entries corresponding to my eigenvalues corresponding to each column. So 1, 2, 2, with the other entries all 0. And so now I have P and D. If I wanted to carry out the rest of the calculation, then I would just have to find P inverse. But to find P inverse, I take P. Let's write this a little bit smaller than that. 1, -1, -1, -1, 1, 0, 1, 0, 1. And I add on the identity matrix to the end of that. And then I'm going to just row reduce this. So to row reduce this, I'm going to get adding the first row to the second row. Gives me 0, 0, -1, 1, 1, 0. And adding -1 times the first row to the third row gives me 0, 1, 2, -1, 0, 1. Now I'm going to flip the first and second row, the second and third row, to get 1, -1, -1, 1, 0, 0, 0, 1, 2, -1, 0, 1, 0, 0, -1, 1, 1, 0. And then multiplying the third row by -1 gives me 1, -1, -1, 1, 0, 0, 0, 1, 2, -1, 0, 1, 0, 0, 1, -1, -1, 0. And then it's just a matter of adding upward to clear out the things above the diagonal, which is going to give me, I wish I had given myself some more space, but it's going to give me adding the second row to the first is going to give me 1, 0, 1, 0, 0, 1, 0, 1, 2, -1, 0, 1, 0, 0, 1, -1, -1, 0. And then adding -1 times the third row to the first is going to give me 1, 0, 0, 1, 1, 1. Adding -2 times the third row to the second gives me 0, 1, 0, 1, 2, 1, 0, 0, 1, -1, -1, 0. So P inverse is equal to 1, 1, 1, 1, 2, 1, -1, -1, 0. Thus our matrix A is going to be P, D, P inverse. And so if I multiplied that all out, I would get back to A. That's the process of diagonalization, and I think that's where we are going to stop for this video.